Hi, this is Kevin Ega, another lecture on Math 141. So we're just tying up the last bits of Gauss-Jordan elimination. Gaussian elimination, it's the material we've been talking about in sections 2.1 and 2.2 of your book. So we're just going to review some of these things and then get to what kind of questions you might have on the test and some examples for you to practice, that sort of thing. So let's first of all review. First of all, solutions to linear systems. One thing we discovered last time was that there are only three possibilities. There could be no solutions, there could be one solution, or there could be infinitely many solutions. So it's impossible for there to be like two solutions or eight solutions or something like that. There's only no solutions, one solution is infinitely many. Okay. Now, let me show you a picture of what's going on here. So let's say we have two equations and two variables. So you got x and y. And you got x plus y equals 2 and 2x minus y is equal to 1. So as it turns out, x plus y equals 2, that looks like a line that's like this. Linear equations in general will look like lines in the plane. 2x minus y equals 1 will be like this. And for these two to both be true, that means we are on both lines at once. That means that we're at this intersection point. Here I've done the row operations necessary here, and in the end we end up with this matrix, and this reads x equals 1, this reads y equals 1, and indeed 1 comma 1 is the unique solution. There's one solution to this system here. Here's another system, 2x minus y equals 1 and 4x minus 2y equals negative 1. Okay. If you turn this into matrices and do all the row operations, you end up here. Okay. And this has a contradictory row. 0 is equal to negative 3. Okay. So there's no solutions. And the idea here is 2x minus y equals 1. Okay, that's one of these. I think it's this one here. And 4x minus 2y equals minus 1 is this one here. And these are parallel lines. So there's no place where they intersect. There's no solution. There's no point that's on both lines at once. So this is no solutions. Here's another one. 2x minus y equals 1. 4x minus 2y equals 2. All right. Here we have two equations, but they're both actually the same, give you the same line. And so they overlap completely. This case, actually, we see that there is 0 equals 0 is one of the lines here. That means one of these equations was superfluous, and you only have really one equation. The other one's just a multiple of the other. You can sort of see this is twice that one if you look at it. And the set of solutions is any point on this line. And you see there are infinitely many such points. If you write this out, you'd see that I've arranged it so that y is the one that's any value. And so you just pick a value of y, just move across, and it's going to hit the point at one place. This is what will tell us what the value of x will be that gives us that value of y. And so there's infinitely many solutions. They can be, basically all they're all related to a value of y. Okay. All right. So, by the way, whenever I have equations that only have x and y in them, that's kind of indicating that I can describe it in a plane. If I've got x, y, and z, of course that would happen in 3 dimensions, and I'm not going to draw that. So, but basically, each equation will be a plane in 3 dimensions. So, yeah, those are going to be harder to draw. So I'm going to stick to systems with only 2 variables here, x and y. All right, here's one where we have 3 equations. Okay, x plus y equals 2, 2x, you can read them. And x plus y equals 2 is this line right here. 2x minus y equals 1 is this one. X minus 2y equals 1 is that one. And you see that, well, they intersect in these 3 points here. Okay, but the idea is I can make these 2 equations satisfied if I just pick that point. I can make these last 2 equations satisfied if I pick this point here, and this one is if I pick the first and third equations. But I can't make all 3 equations true at once. There's no point that is on all 3 lines at once. And in fact, when you do the row reduction, you see this here, and you have a row that's a contradictory row here. And that's how we know. Here's another example. I just changed this number a little bit. Okay, and in this case, we have actually a solution. There's actually this point is on all three lines at once. And the way this worked was basically there is a relationship between these that you can go with just two of these, and that would be enough to pick this point. But in fact, you took all three of them. That's what this row of zeros means. There's basically a superfluous equation. One of these equations might be dropped. Any of these equations could be dropped, and we'd still end up with the same answer. In this case, x equals 1, y equals 1. Okay. That's what that looks like. All right, so let's do a quick review of Gaussian elimination. Okay, we've got three kinds of elementary row operations. We can swap two rows, multiply a row by a number, but that number should be non-zero, and add a multiple of one row to another. Okay, and they do not change the set of solutions. To get a 0, you use an operation of type 3. To get a 1, you use an operation of type 2. All right, to pivot means to get it to be a 1 and use it to clear to 0 the rest of the column. Now, as we know, pivots, they're a little bit complicated. If it's a non-zero, we multiply the row to make it a 1. If it is 0, you try to swap it with the non-zero entry below it, and of course, swap the entire row, not just the entry. And then maybe you have to do this again. If it's 0 and everything under it is 0, then move to the right and give up trying to make that a pivot. And then keep on going. Okay. Once you pivot, right, and then you clear to the rest of the column to 0. Then you move down into the right. So then you go back to this previous step, and you keep on going like this. So let's say a pivot here, make this a 1, everything into the 0. Go down here, make this one a 1, clear everything around and else to be 0. Then go down. I have to give up on this one and move to the right, and then so on, right? Move down to the right. And one thing will happen or another. I might hit the bottom of the matrix. I might hit this side, right? And at that point, we are done. With the result's going to be in reduced row echelon form. Okay. So the kinds of exam problems you might have on this section, you're going to have a bunch of them. There are going to be types that say do the next step in row reduction, or alternatively recognize you already have reduced row echelon form. In other words, that it's done. So you'll be able to recognize that. You need one other kind of problem is just how many solutions are there? Say 0, 1, or infinity. And finally, describe the solutions. So, give the solutions. And what will be given to you is a matrix given in reduced row echelon form. So let me show you examples of all of these kinds of problems here. So here's a problem where you're supposed to do the next step. Okay, I'm gonna say pause, and then you can work it out, and then continue when you're ready to see the answer. Ready, go. And now to continue. Yeah, so this one's already a 1. You don't need to do anything there. We've already cleared these to 0. All of that's done. I now need to go down to the right and make this one a 1. And the proper thing to do is multiply this by 1/2. And that will make this a 1. By the way, some people might be tempted to swap rows 2 and 3. Now, none of the operations that are allowed, none of those will change the set of solutions. So it's not like that would be a bad thing to do as far as getting the answer. But remember, the whole idea here is to make a systematic method. In other words, it's not supposed to depend on anybody's cleverness. It's not supposed to depend on anybody noticing that, oh, look, there's a 1 hanging out right here. No, the idea here is to have it so systematic that you don't have to think about things. And in particular, swapping rows 2 and 3 is not the next step in this process. All right, next question. Look at this, and do it yourself. Ready and pause. And now, if you're done, I'm going to show you the answer. All right, so in this case, again, you've made this a 1, cleared these to be 0. This time we do have this one as 1, and we want to make this one to 0. So I just take -3 times this second row and add it to the first row. And if I do that, I should end up with this. Okay. Now, here's the next problem, and pause. All right, so the answer is this. All right, so we made this a 1, cleared it to 0, went down to the right and looked at this one. This one you're trying to turn into a 1. Do not swap it with a number that's above it, even though it's tempting because it's a 1. No, you never swap this with a row above it, only with rows below it. And in this case, that won't help. So we give up and move to the right and try to make this 2 into a 1. And to do that, you just multiply by 1/2. And there we go. All right. Next problem. So slightly different problem here. And ready and pause. Okay, to show you the answer here, ready? Here's the answer. Yeah, so in this case, you get 1 over here, cleared these to 0. Now try to make this one a 1. We look at underneath it, and indeed, there is a non-zero entry. So we're going to swap these 2 rows. And indeed, that's what happened. Notice that I didn't only swap the 0 and the 9, I've also swapped these other numbers. Oh, wait, sorry, that's supposed to be a 2 and an 8 here. I accidentally did another thing. That's 2 and 8. Right? All right. So actually, there, yeah. Let's try it again. Here we go. And now look at this one. Ready to do this one? And pause. All right. This one's already in reduced row echelon form. This is a 1 here, cleared everything to 0, going down here. This is 0, and everything underneath it's 0. Move to the right. Turn this into a 1. Clear everything else in its column to 0. And then we're done with this matrix. It's already in reduced row echelon form. Okay, using that same matrix, find the solutions. The columns are x, y, and z. These variables, of course, I have to tell you the names of the variables that correspond to the columns here. And pause. And the answer is this. Okay. This one's any values. That's y's any value. And then this is x is equal to 5 minus 3y. Just solving for x. This one says z is equal to 8. And this one is 0 equals 0. I don't need to put that down in my equation. This is x is equal to this, y equals this, z equals this. And that's the solution. Okay. One thing, sometimes students are tempted to solve this one for y. You could do that, except that that's not actually any helpful compared to this. I mean, it's not any additional information. So when you see this, that means y can be anything, and you can plug it into here. If you solve this for y and you put that down, then this is not a way to actually get an answer, because, see, the way we have it here, this tells us exactly how to find solutions. Pick a number, any number, put it in here. Then you'll notice on this side of the equation, we only have things that had any value, in this case y. So once I pick these, plug it in here, and I've got all these other numbers. If I solve this for y and stuck it here, then I would have a circular description. To know x, I'd have to find y. To know y, I'd have to find x. That's no good. Okay, don't chase yourself in circles. Okay, so some students try to do that. Stay focused on how the procedure works. You're only going to solve for these ones that are pivots, and the other ones are going to be any value. Okay. All right, now the next kind of question you're going to have is how many solutions? So each of these things, figure out how many solutions each of these matrices has. You notice that these are already in reduced row echelon form, so no row operations are needed. Ready and pause. All right, I'm going to show you the answers to all of these questions. Ready, and there we go. This one has one solution. Okay, there's a 1 here. And this is the pivot. This is a pivot. There's no contradictory rows, no missing columns. There's one solution. This is infinitely many solutions. These are pivots, but this one here is free to be any value because it's not, we never reached that column. Look at this one. Infinitely many, again, same idea. It's true we have an extra row of zeros here. That doesn't make any difference. Now look at this one. This one has no solutions because we've got this contradictory row here. 0 is equal to 4. And this one has one solution. We've got all these pivots on every column. We never skipped a column. This is irrelevant here. Yeah, so there is no contradictory row, no skipped column. There's one solution. Here's an interesting one. See if you can figure out the answer to this one and pause. And see if you got this one right. This one's tricky. I hope you saw that there's kind of a weird thing about this. There are infinitely many solutions. Okay, it's true that in this problem x is irrelevant, but x is not really irrelevant because I made it relevant when I wrote it out like this. I said this is x, y, and z. I'm calling the columns x, y, and z here. Okay, x is any value, y is equal to 3, and z is equal to 2. Okay. It's true that there was no restriction on what x can be. The equations didn't even refer to it. But you know, if you had a real situation where you actually wanted to know what is x, what is y, and what is z, then there are infinitely many solutions because there are infinitely many choices for x. Okay. By the way, this is infinitely many solutions because this is a solution is when I pick one value for x. Let's say 5. X equals 5, y equals 3, z equals 2. That's one solution. But I could choose x equals 2, y equals 3, z equals 2. That would be another solution. So there are infinitely many solutions. All right. Find the solutions. In this case, the variables I'm calling A, B, C, D, E, A, B, C, D, E here, and pause. All right. Here's the answer. Okay. The pivots are here, here, and here, and these are any value. D and E are any value. You'll notice that D and E are the only things that show up here. That's because everything in the column here, other than the ones, are zeros. That's by design. So when I choose numbers for D and E and I plug them into here, there's nothing circular. Right? Start by just choosing numbers here, sticking them in here. These will give us particular numbers for A, B, and C. Okay. All right, find the solutions for this one and pause. Ready for the answer? Here we go. In this case, the pivots are A, not B, C, not D, and E. So A, C, and E. B and D are any value because those were the ones we skipped. And here we get A, C, and E given by these, just solved for A, C, and E. Here we go, find the solutions. Ready and pause. And ready, and the answer is no solution. This last one says 0 equals 1, so there's no solution. How about this one? Pause. And here's the answer. Again, A is any value. Okay, D is any value, but these are the pivots. So B is equal to 5 minus 2D, C is equal to 7 minus D. You'll notice that once you know A and D, you can plug them into here. Actually, we didn't care about A, but never mind. And we end up with B and C. So that's what the idea of writing the solution like this. All right, so when we get back to campus, we're going to talk about 2.3. We're going to do matrix arithmetic. We're going to learn how to add, subtract, and multiply matrices. It's kind of a fun sort of thing. To kind of take a break from the material we've been doing. We're still doing matrices, but we're doing different things with them. One thing I plan to do is I plan to put together a little bit of a review video for the test that's coming up. So I post that on Friday or thereabouts, and the idea is normally I would have this time when I would review, and the part of it is I just talk about stuff, and part of it is you ask questions. So the part where I'm just talking about stuff, that I'm just going to post, and you can all watch that. And the part where you're asking questions, you can do by email or texting, or use the forums or chat in courses, things like that. And then if you still have any questions, you can address those on next time.